Hi, I'm Alex Nemish. Most of you probably know me. I run a company called Lantr, and we are working on Scalus. It's a dev development platform for Cardano, very similar to Plinth. We just, instead of Haskell, we use Scala 3. We compile Scala to UPLC. We have our CK machine implementation, budgeting, all that jazz. Backends, optimizers, macros, everything you want, and even ledger rules, most of the part, so you can use it if you want. And until recently, we have a CK machine. I measured its performance, and it was all right. It was more or less on par with Haskell CK machine implementation, slightly slower, but not much. And I thought maybe we can do better because I spent like 0 time optimizing it, and I just opened Profiler, spent 3 hours there to fix a few things, and it became like 2 times faster than CK machine in Haskell. And I was like, wow, that's impressive. I can share this result, but I need to check that nothing changed. And I updated Plutus, and apparently Roman spent, I don't know how much time optimizing CK machine, and now it's still faster. But we're, I think we're reasonably close. So that's auctions. It's a Plutus benchmarks, which Kenneth, I believe, wrote. There's auction, there's 4 versions of auctions there. And blue line is previous CK machine in Haskell. Red one is our Scala implementation, and the yellow one is a new Haskell. So it is better, but you know, close enough. But then I thought, so why the JVM implementation is reasonably fast? Because it's a bytecode, you know. That's because JVM uses just-in-time compilation. It measures executions of the evaluations of the bytecode and compiles it to a machine code in just-in-time, in runtime, basically. And it optimizes it for particular data that is being run and a particular hardware. That's the reason why JVM is reasonably fast. And at some point, I thought, wait a minute. So CK machine, UPLC, is a lambda calculus, right? And CK is a virtual machine for this lambda calculus. And JVM is a virtual machine. Like, can we run lambda calculus on the JVM? And yes, we can, because we have lambdas on the JVM. The only question is, how do we load the actual contracts, the actual UPLC, and convert it to these lambdas? And so we need to do like just-in-time compilation of UPLC to then just-in-time compile it to the machine code in runtime. So the thing is, it's possible, because in Scala 3, we have this thing called runtime multi-stage metaprogramming. So Scala allows you in runtime run a compiler and execute macros there. And these macros can be multi-stage. So you can generate macros that generates macros that generates macros that generates code that can be run then. So my thinking was, is it possible to actually load a UPLC program and convert it to lambdas on the JVM and run it, and how it will perform? So like the basic idea here is we have this staging compiler, and we can pass a macros there, and it's gonna just unroll the multiplication and produce this x multiplied by x multiplied by x 3 times. Yeah. So I've made this prototype, basically. So the idea is something like that. So we can compile this very simple expression. For example, it takes an integer, big int, and if it's bigger than 0, it halts, basically. Throwing an exception means error. So we can compile it to UPLC, and then we JIT-compile it to a function, to a Java function, basically, and then we run it. So that's an example. The real thing is more complicated. So here, for example, we take a term. Do you see it, by the way? That's right. And then from that term, you can load it from a file, so it doesn't have to be compiled. You can take a plinth, UPLC, whatever. And then we generate code. So for variable, we generate a Java variable. It's a quasi-codes. For lambda, we generate lambda. And also, we inline the budget computation as well. So this thing actually computes budgets correctly, how it's supposed to be. So, and it halts when the budget is exceeded. Phil?
Say for lambda, you generate lambda, but you're generating JVM code? Is that right?
Yes, exactly.
The JVM doesn't have lambda as an instruction. So
No, it doesn't. It compiles it to machine functions. So it's very fast. Similar to what Haskell does. Applications compiled to, well, function calls, obviously. Well, built-ins, force is application of unit. Delay is construction of closure, basically. Constants compiled to JVM constants. Built-ins compiled to built-in implementations on the JVM, and we even do the inlining and just add integers compiles to x plus y, basically.
How do you handle crash application for built-ins?
You just create a closure, as usual, yeah. So it's very, very straightforward. It's a very simple idea. I'm just surprised that I came up to it first, basically. And I was interested how it would perform comparatively to the VM. And it performs actually quite well. So the green one is the JIT-compiled thing. So it's like 5-6 times faster than highly optimized Haskell CK machine implementation. By the way, and I envisioned two questions before I answer yours. First question is, so why is it fast other than we just compile it to in runtime, like particular contracts? Well, one of the speed advantages is because we use stack. So essentially, these calls are calls on a stack. And the question is, what's going to happen when there's going to be stack overflow? So I computed, we have 14 million memory limit, and we need like at least three evaluations to do recursion. So it gives us, let me see, so like 46,000 recursion calls. So the frame size on JVM is roughly 100 bytes, just guesstimate. Well, it's not guesstimate, I checked, but it's roughly that. So we need like a 5 megabyte stack to completely run it on stack, which is not a problem, I guess. 5 megabyte stacks is not bad. So we actually implemented a hybrid JIT compiler. That's actually what it does. It counts the stack depth, and at some point, if it reaches like 10,000 or something, it can just bail to the CK machine implementation. So we get CK machine evaluation in the worst case. Yes?
So if you go to your timing chart.
Timing charts, yes.
The time for JIT version, does it include the time to JIT, the time shift?
No, of course not.
Yeah.
You pre-JIT it, of course.
If I wanted to use this on my notebook,
times of JITting and then executing the
No, of course not. It's slow. I would never do that. Yes, Phil.
So there are some situations, of course, where you can compile stuff in advance, and that's great. I'm not quite sure why you're using the name JIT for your ahead-of-time compiler.
Because it does it in runtime. It's actually in just in time.
So the reason for doing something JIT is that you have data at runtime that you
Exactly.
know how to compile that.
Yes.
What
Imagine it's a node.
runtime do you exploit?
Sorry?
What runtime data do you exploit?
What runtime data? Scripts. I can receive a transaction. Imagine I write in a node and I receive a transaction with a new script. I have never seen it before.
With a new
Script. Like, if, yeah, new UPLC. Bytes. I just deserialize it, compile it, and I can use it.
Yeah, but just because you're running something at runtime doesn't mean it's not an ahead-of-time compiler. JIT is a particular kind of compiler, which you described. It's exactly what they do for the JVM that makes use of the data structures at runtime. You didn't show anything making use of it. So you could do ahead of time. You just happen to be doing it when you
Yeah.
get the thing.
Yes, exactly.
Right. So it's not a JIT. It's an ahead-of-time compiler, AOT.
But I do it in runtime, right?
That's not what counts. That's not what JIT means.
You're doing it in node runtime, not script runtime, I think is the point. It would be a JIT if halfway through running the script, you then compiled the next bit of script. If your argument is you're running the node and you receive a transaction with a new script, then that JIT compile, in your terms, needs to be included in the script.
So the terminology is not correct, right? Okay, okay.
But more importantly, right, what you just said is what we do, you know, here's what we're doing in practice, right? We want to run in a node. So what we do is we get the UPLC code, we run our ahead of time, I'm going to use my terminology, compiler on it, and then we run the JVM.
Yeah.
So you do both.
Yes.
And then he asked you, did you include the time for running your translator?
Yeah, I
And
think
you said,
No.
no, of course not, because it's long. But
Yes.
you're doing both in the node, so you need to add the two together to fairly compare to the other two, which are running UPLC directly.
Let me address it in the next slide. So my point is that I was curious, like, okay, how, like, it was an idea, can we do it? Can I do it? We can. It works faster. And like, what's the application? So application is, my thinking was that potentially, as usually happens in life, a small number of scripts potentially is responsible for a lot of executions. That was my assumption. So then we can potentially JIT compile or pre-JIT compile these scripts and just use it for cache, essentially cache those. And I investigated 100,000 blocks, and unsurprisingly, 10 scripts responsible for 61% of all execution.
in mine.
Sorry?
Mainnet.
Of course, in mainnet. So like top 100 responsible for 90%. So if we just JIT compile 10, 20 scripts, we can like 6 times speed up the execution. That's a work in progress. It's basically a prototype, an experiment I wanted to share with you, but it works. So basically, yeah, basically. So another. Yes, Phil.
So you could do it that way, and that'd be really fast. That's great. The other thing you could do is just translate it when you get it and run it on the JVM.
Translate.
May
Yes.
not take that long.
Yeah.
So it might be faster than the other. Have you measured that?
No,
Yeah.
no. It's just from the bakery. I mean, we just made it like 2 days ago, so haven't spent enough research in this direction. But we will try it.
Yeah, you should.
I'm curious, and this is not really a question that you can answer, but to kind of the JIT point, if you're compiling it into Java bytecode, I wonder if you could do that in such a way that you're leaving space for the JVM to then do JIT compilation afterwards.
That's the point. So it's a JIT.
That's cool, but that's
Yes.
not what you said, and that's why Phil's upset.
Well, well, maybe I implied that.
Okay,
I implied
but
it.
This is important. You're turning it into Java code, which can then be JIT compiled.
That's why it's fast.
Data, yeah.
That's why it's fast. It's the only reason.
But it's only fast. Yeah. Okay.
Because
I
the,
think it probably is, but the argument isn't.
all right. Is it clear to everyone that we compile to essentially Java bytecode, which then JVM JIT compiles to machine code, and that's why it's fast? Yes.
I have a question, but it's theoretical. Maybe I don't know about the JVM too much. Is it possible if once you JIT compile some code, it's cached somewhere, right, in memory? Is it possible to just throw it away if not needed, or does
Yes. Yes.
Java does it
Yes.
automatically?
Yes.
Right.
Yeah, it's another garbage collection. It works there as well. So a practical application would potentially be L2s. So if you want, like, Hydrazoa is being developed using Scalus. It's a like variant of Hydra. George Flerovsky worked on it, if you know the guy. And they are actually interested in trying to leverage this thing. We haven't tried it yet, but ideally, if you run on L2, if you run a Hydrazoa head, maybe it's a specialized application. It's like you have like 10 scripts that you want to run very, very fast. That could be an application, and Midgard potentially as well. So we can pre-compile, pre-cache the frequently used contracts.
I have a question. So, yeah, so, I mean, as usual, the root of all evil is costing, right?
Mm-hmm.
And this does not, I don't know if this can allow you to lower the cost, the cost.
No, currently it's just a time for evaluating scripts.
Yeah, because you still need to, the costing still needs to come.
Yes, and we generate it. Yeah, we generate the costing stuff, so it behaves the same as CK machine.
I don't think it was like the reason for the optimization was not in order to lower costing, just to optimize for most.
Execution time, yes,
But the
yes,
costing won't get that.
Yeah, so people will still pay the same.
yes, yeah.
Yeah.
Just-
So those very fast execution times that you showed included computing the cost of doing it.
Yes, yes, because otherwise, like 10 to 20 times faster. But that would be unfair, so we had to include this.
After implementation.
Sorry? Yes, yes, for sure. Yes, yes, yes.
Earlier, when somebody asked it, you said, "Oh no, I didn't measure that. Why would I? It would be slow." And Phil asked, "Did you measure the times?" And you said no, but you must have had some personal experience with it. You had some. Do you have some ideas that take about the same amount of time to translate it into the JVM as it is to run it, or?
No, it takes like for a contract. Currently, for some unknown reason, I hope it's a bug in Scala compiler or something. I don't know. It takes like 10 seconds per script. 10 seconds. 10, 12. I don't exactly remember, but something like that.
Weren't
That's
quite clear. Do
too
you
much.
generate?
Like I expected it to take a while, but 10 seconds seems too much.
Too much.
Yeah.
I think if the application is only to use it for, you know, the top 10 or top 20
Yeah,
scripts, then
I'm talking in general. Even
yeah, for
like 10
Yeah,
seconds
yeah.
seems a lot.
Seems a lot. I agree.
Do you generate JVM directly, or do you
No, no.
generate Scala and then use
I generate Scala. I use Scala macros essentially in runtime. So I generate code, Scala code essentially is quasi-code like that, using macros. And then it gets converted.
I understand how you were generating lambdas, because you have
Yes.
lambdas not in the JVM, but you do have them in Scala. So you generate
Exactly.
lambdas and they compile them. That also explains why you're so slow. The Scala compiler is doing a lot,
Yes,
but it's not very fast.
that's precisely.
And this is why you want to describe it as an ahead-of-time compiler, because that's what you had in mind, right? You said take the top 10 scripts, compile them when, not when you get them. But
Yes,
ahead
yes.
of time. It's an ahead-of-time compiler. That's
Yes.
the best way to describe what you're doing to make clear the advantage of what you're doing.
I really wanted to show that we can do this in runtime during like a node execution. So you can receive a new.
It takes 10 seconds.
Yeah, but
Compiling
I'm
them
fine.
and caching them is the exact opposite of JIT, but it's brilliant. But it's the opposite.
If you cache it, we are saving them. It's ahead of time.
All right.
Just-in-time compiler that compiles it to something that can then be
Yes.
just-in-time compiled.
Yes. Yes.
Yeah, so it has both.
Yeah.
Ahead of time.
Yeah.
Yes.
Hybrid
But,
compiler.
so,
Can you generate JVM code directly? So instead of invoking the Scala comp.
Yes, but it's less fun.
Okay. More efficient, but less fun, right?
Yes. I don't know how can we. I'm quite sure we can cache the results of compilation and we just load them. I haven't tried it yet, but we'll definitely will. Yeah. What else? Yeah. If you're interested in stuff like that, join our Scholars Club. And yeah, we'll do session like that semi-regularly. Questions?
if you have fixed the 10 seconds, you have benchmarks of both translate.
No, it's still gonna take some time, and it's not fair. You can pre-compute it before, and the execution time what matters, right? Because it's about nanosecond or microseconds. You're talking about microseconds.
It will be still useful to understand what is the time. Like the interesting time is going from the byte string to the result of the execution. That's the interesting time.
It's not the best case for this technology then. Yes.
Well, it's not really unfair because the
Yeah, no,
Haskell
I
one,
get
the benchmark includes the serialization, which
No, it doesn't. There are three benchmarks.
you could run the one with the serialization. That's what we used to compare with the
But I want to compare CK machine evaluation, right? That's why I take benchmarks of CK and compare it to directly with CK.
I don't think it really matters because it's not realistic to do it on every script anyway because having compilation.
Of course, precisely.
So you
Yes.
have some LFU cache.
Yes. That's essentially a caching. Yes.
Anyway, so you're compiling, 10 scripts a week. So
Yeah. And I think we can do similar technique on the JavaScript VM, right?
That's why I'm asking, because
But I don't.
I read all these, I never tested it though.
Yeah, but it would be reasonably harder, I guess, to do it like in runtime in compiled language. I guess. I'm not sure.
So if this doesn't result in lower execution budget, then it doesn't really improve increase the number of things we can do on chain. It's basically just makes
Yes.
the node run a little bit faster
Yes.
sometimes.
Yeah.
Well, and the thing is in an earlier slide, it was pointed out that one of the really cool applications for this would be L2s.
Mm-hmm.
In which case, obviously, costing is going to be different anyway.
Mm-hmm. Yeah,
If
good point.
the L2 chooses, like if I'm running a Hydra head, I can choose to have basically no cost, and then
Yes.
I will want as fast as possible execution, and probably only for 10 or 20 scripts anyway.
Yeah, that's yeah.
So
Thank you.
Let me mention something quite weird, which is that we have Plutus as a scripting language on chain, but there's provision in the ledger rules to have alternative scripting languages.
Mhm.
So what you could imagine is that you could use this as an alternative scripting language to the standard one, and then execute some scripts with different costing budget
Oh,
using that. Okay.
interesting.
But,
Yeah.
but I'm not convinced you can integrate the JVM with the node.
We need to implement. Well, if we get the budget for a node,
And I'm not convinced we should have a JIT compiler running on the blockchain.
no, I don't see why not.
Why?
We'll have TypeScript node, and it's gonna be JIT compiling TypeScript. So
I think it seems to me like this has limited scope where it could be useful, but in that scope, it could be extremely useful. Because if you're, like I said before, if you're running an L2, you want things to be as fast as possible. And
You won't have the same timing constraints that we have on.
yes, you have way fewer constraints on an L2. So.
Yeah.
even for Haskell nodes, that's not a useless result. It's good to know that you can do it and you can employ different compiler and do the same strategy, right? That's great to know.
You could generate JIT code.
Yeah.
Or just directly some assembly.
the main point of the talk that it just show you that we can do it, basically. It's possible, and it works surprisingly well. Thank you. Yeah, that's it.